Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Last year, but today he's going to talk about some other exciting projects.
Thanks a lot, Pablo. Good morning, everyone. So today I will talk about complex communication networks, emphasizing on the issue of studying the algorithmic performance of basic algorithms and protocols that are run on these networks. I will show how to use and extend the spectral method approach, which is a method that we borrowed from graph theory, to answer questions related to the performance of algorithms and protocols on these complex networks. And as a concrete example, I will show how to analyze the performance of basic construction and searching schemes in unstructured peer-to-peer networks. This is work that I have done with my advisor, Milena Michail, and I have the pleasure to work and collaborate with other faculty and researchers. So, probably most of you have seen complex communication networks. Examples of such networks are, for example, the internet at the level of autonomous systems, a visualization of which I have in this slide, peer-to-peer networks, the World Wide Web, and many others. These networks have been built with the purpose of implementing some basic functionality which is different in each of them. For example, in the internet, what we want is routing. In the case of peer-to-peer networks, we are very interested in searching. However, all of them have some common characteristics, and they are characterized by the term complex because they have these characteristics. For example, all of them are unstructured, and there is no central authority that controls how these networks are constructed, how the topology of these networks looks like. And moreover, in these networks, each node, each autonomous system in the case of internet, each computer in the case of peer-to-peer networks, makes decisions independently. So there is no common goal that all of them try to achieve together. It is quite surprising that despite this decentralization, these networks have managed to scale from a few hundred nodes to a few thousand nodes in the case of the internet, or to some millions of nodes in the case of peer-to-peer networks, quite efficiently and without collapsing. So there should be some good things with these complex networks. And this particular scaling performance is one of the big focus of the study, and I will show some results later. From the technical point of view, observe that these are quite sparse networks. So in each of them, each node knows only a constant number of other nodes on the average. So in the case of the internet, an autonomous system communicates with, on the average, around 3 to 4 other AESs. However, there are some networks that have very large degrees. These ones, in the case of the internet, can be big ISPs, and in the case of peer-to-peer networks are ultra nodes. Now, many researchers have tried to answer various questions on these networks. For example, particular examples are how and why they have managed to scale such efficiently without centralized control and in so little time. And unfortunately, these are very important networks, and we are interested to study the performance of these protocols that are on these networks. However, there are not good analytical tools that will help us reason about that performance. And some researchers have tried to take different approach for how to quantify the performance of these communication protocols. In all of these cases, it has been observed that the topology of the underlying graph is very important in studying that performance. And it is quite important to study the topology of these protocols. And obviously, from a computer science perspective and from an engineer's perspective, we are quite interested in not only understanding how these topologies and how these networks look like, but in building protocols and algorithms that take advantage of the characteristics of the topology to implement efficient algorithms. So, in my research, in the research I have done, I have used the method of spectral analysis to answer these questions, to answer questions that have to do with how the topology looks like, how it does scale, and to help me understand how to build protocols that take advantage of these unique characteristics. The spectral analysis method is borrowed from the graph theory, and I will introduce it as we go in the presentation, but you can think of it as a basis transformations. It is quite similar. Spectral analysis is to graphs and topologies what Fourier transforms is for signal processing. So it is the exact analogous for the domain of graph theory. And in answering these questions, I have, with my advisor, we have done some research on starting by trying to understand the nature of some fundamental properties of the topologies, which have important effect on the performance of algorithms. And these are clusters, or better, groups of nodes that have good high connectivity with each other, but sparse connectivity with the rest of the network. In an Infocom 2003 paper, we have actually studied the effect of clusters, but most importantly, we have defined some metrics that will help us analytically reason about the effect of clusters. Then, in a sigmetrics paper, we have studied the impact that the clusters have on the performance of the network, and more importantly, how the performance of the basic communication protocols scales as the size of the network increases. Recall that the internet has increased almost by a factor of 5 from 97 to today. So we are quite interested to see whether the protocols that we run scale well and whether they will continue to scale well as the internet increases, or similarly for peer-to-peer networks. And quite recently, we have moved into the study of of taking advantage of our understanding of these topology characteristics to implement and design algorithms for topology constructions for peer-to-peer networks and for searching. So, in the rest of the talk, I will describe this line of research, and this is a short outline of the rest of the presentation. I will start by introducing the spectral clustering method and how we have used it and adapted for the study of communication networks. And I will define two metrics, namely conductance and eigenvalues, that will help us measure the effect of clustering. Then I will motivate by the use of the internet autonomous system level to study whether these clusters actually exist in the topology, and they do, and to study the nature of these clusters. And then I will show how these clusters actually affect the performance of scaling of the basic protocols. And in the second part of the talk, I will actually give more details of how we have used that to design protocols and algorithms. So, as you can probably, if you have studied this kind of communication networks, maybe it is possible that you are familiar with the concept of clusterings. In all networks, there are nodes that have some close geographical and business relationships that tend to communicate and connect with each other more oftenly. So in the case of the internet, for example, we can have, a cluster of nodes of AESs in Great Britain, or cluster of nodes of universities, let's say in France, and so on. However, even though it is intuitively easy to understand that this type of clusters do exist, it is quite difficult to quantify them and to have a proper measure for them. So one interesting question is how to use what is a clustering definition, and over the last years, many of them have been developed. The other interesting question is how to discover them. And this obviously depends on the clustering definition. But most importantly for our line of studies, to study how these clusters will affect the performance and how to use them in our advantage for design purpose. So we have used the concept of conductance to measure the effect of clustering. So think of conductance as a measure that, here I have a definition of it, think of it as a measure that defines how a subset of nodes connects to the rest of the network, and it measures it measures the number of links that exist from this subset to the rest of the network over the size of the subset. So the important thing that you need to keep in mind for this talk is the higher the conductance, the larger number of links that will exist between each subset of nodes. And in general, this is good. It means that the topology is not partitioned. So, yes? Yes. Yes. There are many other, clustered metrics that we have used in the past, like the clustering coefficient. The good thing with this particular one is that it measures global characteristics of the topology, whereas other ones measure local characteristics. And for that particular one, it is easy to relate it in order to study the performance of basic routing and basic searching in the topologies, whereas the other measures, they don't have a direct algorithmic implication and significance. However, even conductance is a measure that it is difficult to compute because finding it is an NP-complete problem. The good thing is that there is a metric that it is easy to compute algebraically, and this metric is related to conductance. This is the second eigenvalue of the topology. For that purpose, this term comes from the algebra, but for the purpose of this talk, and actually you need to you need to remember one particular thing. If you have the topology of the network, it is algorithmically very efficient to find some numbers, which are called the eigenvalues. And the definition of these numbers is as here, where A is the topology of the network, is a matrix that describes the topology of the network, and these eigenvalues relate to the measure of conductance. So if we have a topology and we measure a good conductance, then by the first inequality we can observe that we will have a good, if we measure good eigenvalue, an eigenvalue that it is bounded away from 1, then we'll know that we'll have a good conductance as well. Also, if you're familiar with the Markov theory, you will observe that if we have a network with good conductance, then the second eigenvalue is bounded away from 1, and this means that some basic Markov chains on the graph will be rapidly mixing. So actually, let me go back to also note something, that apart from these eigenvalues that we can compute, there are some associated eigenvectors that can help us identify these clusters. So in a particular example, you can see that the eigenvectors will be functions on the nodes and will assign positive values on one cluster and negative 0 values to the rest of the topology. Yes? Yeah, actually, it is not exactly the adjacency. We take the adjacency matrix and do some transforms on that have meaning in the context of communication networks. But more or less, it is the adjacency matrix. Actually, it is a stochastic normalization of the adjacency matrix, to be more precise. So if we take, these eigenvalues, we see that they can help us identify clusters. What is particularly interesting is that the set of the eigenvalues, which is usually referred as the spectrum of the topology, is a metric that has been invariant over the years. So despite the fact that the internet has grown a lot, this set of these eigenvalues haven't significantly changed over the years. And this actually tells us that at least, despite the growth, we have some invariants that we can use to reason about how the network evolves. Yes. Y-axis is order. So we take the eigenvalues. Oh, the Y, sorry. It is eigenvalues, sorry. It is eigenvalues. So the eigenvalues observe that they take a value from 0 to 1 in our definition. Sorry about that. So if we try to examine what are, the eigenvalues signify that there are some groups of nodes. And we can use the eigenvectors to identify this group of nodes. So here I give you two examples of groups of nodes that can be extracted from the eigenvector, from the eigenvalues and the eigenvectors. In one of them, we observe a cluster of Greek academic networks in Greek and other universities in the Balkan area. In the other cluster, we can see some big ISPs in Europe. So these clusters that we have observed in the topology have some natural, geographical, and business-related reasons why they exist. And we'll see that because they exist, they have some important implications on the performance of protocols. So this spectrum of eigenvalues and this separation of the second eigenvalue from one is not something that has been observed only in the case of real data and topologies like the internet, but it's something that also exists in other cases, like, for example, graphs generated by other models like Waxman and INET and other ones. So the spectrum and the separation of the second eigenvalue from the value of 1, so the second eigenvalue is always smaller than 1, and it is not really, it does not get arbitrarily close to 1, is a common characteristic of main topology generators. If we want to, and here I show that for when we studied both topologies and even if we study subparts of the topologies, we'll see that this same behavior and this same characteristics also exist. Now, let's try to see what is the implication of this pattern of eigenvalues on the performance of a basic task. We'll do the following experiment. Assume that between each pair of nodes in the topology, we have a unit of demand that we want to route. And we route this demand along an optimal, let's say, shortest path route. Then we measure for each link how much of the demand goes through that link. Obviously, we take, in this particular experiment, we take the load of the most congested link, and we call that the congestion of the network. This actually is not really, it is not really directly related to the congestion as defined in the context of, let's say, TCP connections, but it has some important characteristics, and it is a term that it is used extensively in graph theory. In this particular experiment, what we do is the following. We do the experiment, we measure this congestion. Then we identify the clusters of nodes, and we try to route more traffic inside each cluster. So in this particular case, 20% of the traffic is routed inside the cluster, so one node to another node in the cluster, and the rest, 80%, is routed uniformly across the entire network. This will have as effect the decrease in the load of the most congested link, because these congested links are the links that connect clusters. And we are interested to see how this congestion will drop as we increase the intra-cluster traffic. So if we increase the intra-cluster traffic to 20%, we see that the congestion drops to 91% of the original congestion of the case of uniform traffic. We see that as we increase the amount of intra-cluster traffic, in all the topologies, we see a drop in the congestion of the most congested link. And yes? Yeah, it is shortest paths in this particular example. Yeah. So it is important, you can think of it as the internet is built in such a way so that to make sure that you have a lot of capacity inside, clusters between, let's say, Greek universities, and then the capacity actually drops with other nodes that you don't interact that much. Actually, if you take these results for the case of the internet and you compare it to the real results, you will observe that the links that they are the ones that have the highest congestion are the ones that people usually complain about that they don't perform well in the internet. So things like transatlantic links between big ISPs, and so on. So this experiment actually shows that as the intra-clustering traffic increases, then the congestion.
Understand if there is no clearly on the internet.
No, actually, yeah, it's a valid question, but we haven't really assigned all the nodes into clusters. So there are nodes that are not. So in this particular example, it is a heuristic that we have used to assign clusters, but to find groups of nodes. But we haven't really found all the groups of nodes. This actually is probably we have around 200, around 1,000 to 2,000 nodes out of 16,000. So it is a small percentage of, it is a good percentage, but quite small of the nodes that belong into clusters. So recall that this, using the eigenvalues and eigenvectors can give us only heuristics. So, in some cases, clustering is not something that can be observed. There are some networks that are well connected, and we cannot infer clusters to this type of experiments. So then, we have seen this type of clusters in the real topologies, and we are interested to see how this type of effects will scale as the internet grows. So as we increase the size of the number of nodes in the network, how the congestion of the most congested link will scale. Again, we assume the same experiment, but now instead of studying one particular topology, what we do is we increase the size of the nodes in the network and see how this congestion, and we try to quantify how the congestion will increase. Observe that since we have n nodes, the maximum, there are n square, almost n square pair of nodes, and this means that the maximum load can be n square. Since the network is sparse, we have also order n links. So, however we do the routing and however the routing looks like, there will be at least one link that will have order n congestion, only because it is n squared over almost n, order n, the number of links. What we are interested in is to see whether the congestion is closer to that case, which will be good for the scaling of the topology, or closer to that case. And we have shown in the schematics paper that it is actually closer to the n case. We have shown that the congestion grows as n times log square of n. We have proven that by using a well-known result by Layton and Rao, which associates the congestion of the most congested link with the conductance of the topology. Using a probabilistic counting argument, we have shown that good conductance for such topologies, and which, we have actually shown this result, which actually, using the well-known result by Layton and Rao, implies that the topology scales well. And also we have, by the connection between the conductance and the second eigenvalue, we have a bound on the eigenvalue. Yes? Yeah, actually, I write here parallel random graph because it is most people understand, but our result actually is more powerful than parallel. So it applies to every type of model as long as there are two assumptions. One of them is the minimum degree is 3, and in the case of the internet, we actually make up for this thing by increasing the load, and that the maximum degree in the topology is a square root of n, which is also common in the power law random graphs. But the result is actually more general than the power law random graphs. No, no. I mean, this is a good result. It says if you have a power law degree, if you have any degree sequence, as long as these conditions are met, you will have this good result. Which intuitively you can think of it as that there will be many links in the topology, and you will be able to find good routing in the topology. So we have seen that there are some groups of nodes that exist naturally in the topology, and we have seen that this group of nodes affect the performance, but still the performance of the network actually manages to scale well based on the previous result. So this actually has many implications on the algorithm design problems. If we were to design or to evaluate algorithms that use these characteristics, how we could have done it. So we have actually, I'll show you some results that have to do both with the algorithm design and also answer the question of how to maintain topologies that have these good characteristics. So not only we want to generate efficient algorithms, but if we have the power to control how the topology will generate, we want to make sure that deterministically the topologies will have the good characteristics. What is a surprising consequence of the good connectivity of the underlying topology is a result that says that in these topologies it is quite efficiently to perform uniform sampling. Observe that you have a very large network and you don't know what are the nodes. You don't even know how many are the nodes, but still you would want to pick nodes uniformly at random. Obviously, you can think that this is not possible. However, because of the good connectivity, it is quite easy to perform this uniform sampling. To have an algorithm that picks nodes at random and have good characteristics that this sampling process resembles uniform sampling. What is the interesting connection is that this uniform sampling is a principle that is used either implicitly or explicitly in both the algorithm design and the topology maintained processes. So in the next, in the second part of my talk, I will actually talk about this particular topic of how to design algorithms that take advantage of these topology characteristics, and for two particular, and I will show some examples of two particular cases. The first is how to maintain topologies with good connectivity, and in topologies that have good connectivity, how to do efficient searching. And this will be described in the context of peer-to-peer networks. You have a question? Oh, no, it's okay. The uniform sampling. Okay, so if we do, for example, topology maintenance, I will show you a little bit later, but in order to construct a good graph, you would have, if a new node wants to pick some neighbors, it would be better if it could pick neighbors uniformly at random. This will guarantee that the topology will have good characteristics. For the case of searching, this is also quite interesting property. So it tells you that no matter how the topology looks like, if you can search by simulating uniform sampling, you are guaranteed that you will get results that are close to the expected value for the network. So imagine that you are at this part of the network and then the results are somewhere here, but you have no idea where they are. If you do, let's say, basic searching around your area, you will not find them. But if you can do uniform sampling, you will find it. I will give you some extra details. I mean, the rest of the talk will elaborate more on that particular question. Yes, exactly. So first I will describe the question of topology maintenance. So there are many important unstructured networks that are commonly used today, and these are the peer-to-peer networks, which are gaining in popularity. However, when we want to design such networks, we want to make sure that the underlying topology have some good characteristics. So this, in terms of peer-to-peer networks, translates to people being able to find the content that they are looking for. In graph theoretic terms, these good characteristics usually can be translated as connectivity. So the underlying network should be connected so people can find each other. And moreover, it is always assumed that a desired property is low diameter. So if the diameter is small, then there are good chances of finding other people that may have content that you are interested in. We actually, in our study, we use a third property, which is good conductance, and which means that there is good connectivity in the underlying topology. And this particular property actually subsumes both connectivity and low diameter. So if a network has good conductance, then it is connected by definition, and it also has it will have low diameter. So the problem is how exactly can we design networks that have these properties, and how to design efficient algorithms, efficient distributed algorithms to do that. So assume that we have a new node that arrives in the network, and that new node wants to connect, let's say, to 3 other nodes, because if you think of it in the case of peer-to-peer networks, when a new node arrives, then that peer wants to connect, if it is a lift, to around 4 to 6 other nodes. How can that node pick these nodes? And we know from basic graph theory that if you could pick these nodes uniformly at random, then you would have a topology that it is a perfect expander, and a topology that has this good conductance. Observe that in this context, and in my talk, I will not really mention about other properties of the topology. For example, what are the delays or the throughput between pair of nodes. But the schemes that I will describe can be extended to take this type of effects into account. But now, for simplicity, we are interested only in constructing topology that has good conductance and good connectivity. And not only that, but we want to do that in a distributed setting and do it efficiently. Yes? Yeah. To give you things more efficiently. Yes. These schemes are also quite easy to extend in that particular domain. So, but in order to guarantee good connectivity for the whole topology, if you could have 3 or 4 connections that are uniformly at random, then you could do that, independent of what you would do in your other connections. So, we have proposed an algorithm that actually tries to maintains a topology with such characteristics. And in our proposal, we have assumed that there are some daemons that walk around in the network, going from a node to neighboring nodes at random. So these daemons can actually move the next step to either of these 3 nodes. So a network can have many daemons that are maintained, for example, by the ultra peers. But for the purpose of the illustration now, we'll assume that a new node wants to connect to 3 random neighbors, and so there are, to D random neighbors, and so there are D daemons that walk around. So upon arrival of a new node, the daemons move around the network. The new node actually contacts the ultra peers that maintain the daemons and find their local current locations and connect to them. In the next step, when another node arrives, then it has to wait for the daemons to make, to move a little bit and connect to the next location of the daemons. So, in this particular application, we have these daemons moving around and people joining their location. But it's important that the daemons make some steps before joining. There was a similar proposal that was. There was a similar algorithm that was proposed in the Infocom 2003 paper, but in that algorithm, they had the daemons actually have to move log n steps before finding a proper node to connect to. We show how in our scheme actually we have this cost actually reduces to a constant factor. So not only we don't need to make log n step, which is in any case it is difficult, especially since we don't even know when, but we have in our scheme is much more efficient. It tells us that we have to make sure that the daemons move a constant number of steps, and this constant can be as low as one step. Yes? Yeah. 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 Not really. Okay, in that particular example, we assume that most of them have all the nodes have more or less the same degree. But in general, this is not really a problem as long as it is bounded, the maximum degree of a node. So if there are it's bounded, it will work perfectly without problems. Yes? It is undirected. And observe that it is not exactly Markov chain in the regular. It is random walk. It is a Markov chain, but there is a kind of extra difficulty is that when a new node arrives, then the network changes because you connect it. So it is not. It is in the same. Yes, it is reversible. So it is intuitively you can think that there should be, very high dependencies between the arrival of successive nodes. So nodes that arrive one after the other, they have high chances of being connected close to each other. And you can think that this may imply clusterness. And clusterness in that case in a very bad way. And indeed, you can, if we examine the connectivity matrix of the topology, we observe that consecutive nodes have higher chances of connecting to each other. This is clear by having more dots around the diagonal of this connectivity matrix. Okay, in this matrix, there is a dot in position ij if nodes I and j are connected in the underlying topology. However, the good thing is that there are enough dots that are away from the diagonal, and these kind of connections are the ones that guarantee the good connectivity of the underlying topology. So if we want to actually study the performance of the resulting topology, we'll revisit again the case of the eigenvalues, and we'll actually measure. We have done the experiments of growing topologies using these algorithms and measured the second eigenvalues of the resulting matrices. Observe that in order for the topology to be good, this second eigenvalue should be far away from 1. So it should be not 1 minus epsilon. Here I give some examples of this particular eigenvalue for different sizes of the topology up to 5 million nodes. And in all cases, so here I have, I make the random walk, each daemon make 5 steps before allowing a new node to connect to. In that case, 3 and 1. In all 3 cases, with a constant number of steps, this second eigenvalue is bounded away from 1, so which guarantees the good connectivity. If we compare it also to the optimal case of if we were able to connect nodes at random, then the resulting topology has quite similar resulting topology has quite similar characteristics. So the second in terms of the second eigenvalue, the topologies are quite close. Even to the case that of using more messages that the other group has proposed, which actually gives results closer to being able to pick nodes uniformly at random, but by using a lot more messages. So with this simple construction of the d-daemons, it is possible to generate topologies with very good characteristics and with eigenvalues that are bounded away from 1, which means good connectivity. In this one, I think it is 3 or 4. So all the nodes have degrees around 4. but it's in the paper more details of. So the second problem that we are interested in is the case of searching. So assume that the green node wants to find an object that exists in these 3 blue nodes. In the traditional case searching in peer-to-peer networks, the technique used is flooding. So the green node will actually send query messages to its neighbors, and these neighbors will forward the messages to their neighbors. And eventually, if the TTL is 2, this blue node will be discovered. However, another approach for implementing this searching is by the use of random walks, and these are the random walks are the ones that will simulate uniform sampling. And this actually a scheme has been proposed previously, both in its original form of visiting nodes one after picking neighbors one after the other, uniformly and randomly. So the green node sends a query to that guy. This guy has 4 neighbors to choose from, forwards the query to this guy, and so on. And there have been also proposals for biasing the random walks to improve its performance. However, in the previous work, it has never been clear what are the analytical reasons for why the random walks perform better than flooding. It has been argued that random walks are better because they are more configurable in terms of termination conditions. So if you want to create 30,000 messages to find a copy, you have the control to say, okay, 30,000 messages will be generated. Whereas with flooding, you don't have that control. The number of messages increases exponentially to the TTL. But in Infocom 2004 papers, we have shown that there are also analytical reasons why random walks perform well, and moreover, we have shown that even under the assumption that both flooding and random walks use the same number of messages, still random walks perform better. And I will show you these results. Moreover, in a more recent work, we have proposed some hybrid schemes that take advantage of both of floodings and random walks. Observe that random walks is a sequential process, so it takes a long time to terminate, whereas flooding is something that can terminate quickly. We have shown proposed algorithms that have small termination times and still give performance close. Still have good performance close to uniform sampling. So the underlying reason why is that it is because random walks manage to simulate efficiently uniform sampling. There are some, assume that you have the topology and you want to find as many nodes as possible. If you have the power to pick nodes uniformly at random, then in order to examine all the nodes of the network, you would have to use n times log n messages. It has been shown that if you do random walks on that topology, then the expected time to visit all the nodes will be in the order of n log n over 1 minus the second eigenvalue. So if the underlying topology has good connectivity, which is true for most of the communication networks that we have seen, so if lambda 2 is a constant less than 1, then both times are more or less the same up to a big O notation. And this actually property says that random walks efficiently simulate uniform sampling, and this is why they are good. So in order to give you more illustration of how this why searching with random walks actually performs well in this topology which have good clusters, some clustering, I will use the following example. We have a network that has some clusters, but there is also some connectivity, some intra-cluster links that guarantee good connectivity. If we were to perform flooding, starting, let's say, from that node, then a large number of messages would have been generated inside the cluster. And these are kind of redundant messages, because this node actually either has sent or received the message for 3 times. However, if we were to use a random walk, then the random walk has better chances of actually hopping from cluster to cluster and visiting more nodes. This is it is true that even in that case, it is possible that a node will be visited multiple times, but both theory and experiments have shown us that the chances of moving between clusters are better than they are compared quite favorably to staying in the same cluster and generating extra messages. And because of that, in cluster topologies, random walks have this performance. So we have actually done some experiments to measure this the searching performance, and we have in these tables I have some statistics of the number of hits that we got. We can see that in both, in two cases where we changed the number of copies that exist in the network, the random walks gave better performance than flooding in terms of the expected value. But more importantly, we observe that the standard deviation of random walks is smaller, which means that the expected behavior, the behavior of each node doing the searching, is closer to the expected value. And this is good, especially when searching for nodes that are not that are relatively rare, in which case the performance of finding at least one copy of the object is much better in the case of random walk. So the performance of not finding the object, even though there is a node that has that object, there are nodes that have the object in the network, is 3 times better when we use random walks. And this is because random walks simulate the uniform sampling, and uniform sampling has this better behavior. Yes? Yeah, in both cases, the algorithms use exactly the same number of messages. So there is another kind of scenario in which random walks searching with random walks perform better than sampling, which does not have to do something with the underlying topology, but highlights one other characteristic in which random walks are better than flooding. And this is when we have dynamic topologies. We know that peer-to-peer networks are quite dynamic. So new peers arrive and leave the system all the time. When some nodes they are interested in searching for an object, they can ask, what they currently do is ask their neighbors for that object, and at a later point of time, usually they ask again. And the reason is that some nodes have left the horizon, the proximity of that node, but new nodes have arrived. So the node that is interested in finding something has some chances, by repeating the query, of finding more objects, because it can examine the flooding will reach new nodes. However, even though the topology changes, a large number of nodes, they are still in the proximity of the original node. So a large number of queries that will be wasteful, will be duplicate. If we were to do a random walk, then each random walk would follow a different trajectory in the network. So the amount of visiting some nodes over and over again would be kept to a minimum. And so even in that respect, we have observed doing some experiments that random walks have compared very favorable to flooding. So in that case, we have, for topologies of different sizes, we have seen that both in terms of the expected number of copies found and the failure probability, random walks do better by a factor of almost of more than 3. So I will actually quickly discuss some recent work that we have done, and as I have in this context in this algorithm that we have proposed, try to combine the good things of both random walks. I have said that random walks, have better performance, but it is quite easy to see that they have also some big disadvantages. One of them is that they are sequential processes, and that does take a long time to finish. Another possible solution that has been proposed by some people is to use many random walkers, but even this approach actually will have a long finish time. Another disadvantage is that some malicious user can destroy the random walks, and then this means that the random walk will not actually go over. And using many random walkers can also solve this problem. However, is it possible to get the same performance in terms of number of messages as random walks, but with a scheme that finishes much faster than the real random walks, and it is very close in terms of finish time, in terms of flooding. We have seen, actually, we have proposed some schemes that actually do the job. So, in one of them, we do a random walk, but every time that we visit a node, we perform some small floodings. And we see the nodes that are close to that. We have also proposed another scheme that it is actually an extension of, it is a generalized scheme that can describe both random walks and flooding. And in that scheme, we do floodings, but we try to push more messages over links that connect clusters, so that we don't have a lot of repetition of messages inside each cluster. And I quickly examine both schemes. So in the case of doing these random walks with short floodings, we have shown that if, you observe that if the topology does not have any clusters, first of all, this will give you some constant improvement on the performance, because you always see the neighbors. And so if you do, let's say, 500 steps, and each node has 4 other neighbors, you will see around 1,500 neighbors. However, in topologies that have some nodes that have very high degrees, and this is typical case in communication networks. For in this particular case of peer-to-peer networks, these are the super nodes. We have shown that using only square root of n of steps, it is possible to visit almost all the nodes in the graph, almost surely. And the main reason is that the random walk actually biases towards the nodes that have the largest degree. And these are the nodes that will give a lot of information back. Observe that in this scheme, we use locally available information to improve the performance. So what we require is that each node knows only about its neighbors, which is required only for connectivity reasons. Another scheme that it is more generalized is the following. We assume that there is a budget, and this actually tells you the budget is an upper bound on the number of messages that the searching is allowed to use. So when a node receives a query with a budget, then it reduces the budget by 1 and then divides the budget along its neighbors. So if you think of it in and forwards, the query with the new budget. So if you think of it in terms of random walks, you can think that the number of messages is the budget, and then each node reduces the budget by 1 and forwards the query with the remaining budget to one of the neighbors chosen uniformly at random. Similar type of observations apply also for the case of flooding, but in that case, it is only an upper bound. However, the trick of this approach is the following. What we want to do is try to push queries with higher budgets along connections that connect, along links that connect different clusters. In doing so, we try to reduce the number of duplicate messages in each cluster and manage to try to search for more nodes. So we have used some the concept of edge criticality that has been proposed some time ago in the context of in many contexts, including the case of VLSA routing. And in this scheme, we have actually used some only local information to assign. We have used some heuristics based on local information to assign edge criticalities, and we have actually implemented this algorithm based, the algorithm that is forward queries to edges that have higher edge criticality. We observe, actually here I give some results of the performance of this approach. Observe that we have managed to reduce the mean response time to a very small number, which is compares comparatively with flooding, and it is significantly much better compared to random walks. And still, we got quite good performance. It is quite interesting to observe that the performance increases as we bias the searching to go towards edges that connect different clusters. However, actually, if we continue biasing this thing even more, at some point there is a sweet spot. It is a little bit after the 10th power, and then the performance actually drops. We are still doing some work on understanding better the performance of this type of schemes. So in this talk, I have shown to you with some experiments that clusters is an important property that exists in many topologies of current communication networks. And I have shown how we have used and adapted the spectral clustering approach to measure this traffic. I have used two concepts borrowed from graph theory, the conductance and the eigenvalues, to measure the clusters. And it is the reason that we have used these ones is that we have managed to take these metrics and relate them to the performance of basic algorithmic protocols run on these networks. I have shown you how these clusters affect the scaling behavior of these communication networks. And I have told you that these networks scale well, which is a good positive result. And then I have used the knowledge that we have gained from studying the topologies to study specific algorithms for searching a topology construction in the context of peer-to-peer networks. So apart from this work, I have also done some work in some other areas that are slightly related. The first one, or more related, the first one is some work that I have done here at Microsoft with Pablo on some encoding techniques to accelerate the file delivery to a large number of nodes. This is resulted in both a system that have been almost implemented and in an Infocom 2005 paper that is to appear. I have worked on the problem of large-scale content distribution, in which I use basic techniques for content distribution without any encoding and any other extra schemes. And a little bit related to topology analysis, I have also done some work on topology constructors, and we have proposed with my advisor some very adaptive methods for constructing network topologies that have a wide variety of that have some specific characteristics, and still, still the user of these topology generators is able to configure to get different amounts of clustering based on the type of experiments that this user wants to perform. So in the future, I'm quite interested in continuing studying complex communication networks and studying the algorithmic performance, the performance of basic algorithms and protocols on this network. And I want to, it's quite interesting to see how only with the use of local information, we can accelerate the performance of many communication networks. I'm also quite interested in, in a different type of problem that appears in content communication networks. So far, I have shown you in more detail the case of topology construction and searching, but content delivery is one of the most fundamental problems that we have to deal with, especially, companies like Microsoft that you need to distribute a large number of content to many users. And I have started already some work on that with Pablo, and I'm planning to continue on that. And I'm also very interested in extending this formal framework that I have used to study the other communication network, to study some more emerging networks like sensor and ad hoc networks. These networks, they will have to design more efficient algorithms for them, especially since the resources in them, they are of great value. And especially in the case of these sensor and ad hoc networks, studying the topology will have a greater probably impact compared to what it have in other types of networks. So we are working on extending our formal framework for these networks. And quite independently of communication networks, this type of approaches and the study of complex networks has been also used to study other types of non-communicative networks, like, for example, biological networks. And we have already started working on studying the properties of some protein-to-protein interaction network and some protein-gene interaction networks. And we want to see how we can extend our spectral method to give us some interesting information for this type of networks. So, any questions?
I think we're almost Take it offline. Thank you.